Okay, I'm going to start chapter 11 here now. In chapter 11, we're going to do 11.1, 11.2, and 11.3, and then 11.5. Okay, so we'll skip 11.4. The topic here is probability. Now, a lot of what we talked about in the last chapter is related to probability, the counting techniques. Okay, so something to keep in mind there. Definition: probability describes how likely it is that some event will happen. If we look at the proportion of times an event has occurred over a long period of time or over a large number of trials, we can be more certain of the likelihood of its occurrence. Okay? In probability, an experiment is any process with uncertain results that can be repeated. Okay? So if you flip a coin, or if you roll a die, okay, those are all things that can be repeated. The sample space, which we'll call capital S, of a probability experiment, is the set of all possible outcomes. Okay, here's some typical sample spaces in probability. So determine the sample space for each experiment. Problem 1: roll a die. Okay, so if you roll a die, there's 6 sides on the die, 1, 2, 3, 4, 5, 6. And of course, we're using set bracket notation. The sample space is a set. Okay, so be sure that you do that. Problem 2, answer a true false question. Okay, so the only 2 outcomes are true or false. Okay. Problem 3, flip a coin once and let H denote heads and T denote tails. Okay, so if you flip a coin once, you get heads or tails, H or T. Flip a coin twice. Okay, well, both the flips could be heads, or you could get 1 heads and then 1 tails, or 1 tails and then 1 heads, or both flips could be tails. Okay, what if you flip a coin 3 times? Okay, well, all 3 flips could be heads. The first one could be tails, and the next 2 could be heads. Or you go heads, tails, heads, or 2 heads and then a tails third. Or you could go heads, tails, 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 heads, tails, or tails, tails, heads. Or, of course, all 3 flips could be tails. Okay, so there's going to be 8 elements that you list for flipping a coin 3 times. An event is any subset or portion of the sample space. Events are denoted using capital letters such as E. Okay, so what if you roll an event, or write an event as a set? Okay, what if you roll a single die and let E be the event that you roll an even number? Okay, well, on a single die, the only even numbers are 2, 4, and 6. Okay, again, make sure you're using set bracket notation when you list those outcomes. Problem 7, select a month and let event A be the event that the month begins with the letter J. Okay, so as a set, January, June, and July would be the months there that I'd list. Okay. Problem 8, roll a pair of ordinary dice and assume that the dice are easily distinguishable. Perhaps one is red and the other is green. In the ordered pair little r, little g will represent the number showing on the red die. Little g will represent the number showing on the green die. Okay, part A, determine the sample space. So starting with the red die, what if you roll a 1? Okay, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. And then what if you roll a 2 on the red die? 2, 1, 2, 2, 2, 3, etc., all up to 2, 6. And then a 3 on the red die, so 3, 1, 3, 2, etc., up to 3, 6. Then 4, 1 through 4, 6, 5, 1 through 5, 6, 6, 1, 6, 2, 6, 3, all the way up to 6, 6. Okay. Again, make sure that using set bracket notation whenever you have identified the sample space. Also, for this problem, we're using ordered pair notation. okay, which is important. And so there's 36 outcomes for rolling a pair of dice, okay? Now, part B says, let event A be the event that you roll a 9, right, as a set, okay, using a pair of dice. So what are all the ways that you can roll a 9? Well, I'm not going to list like 2, 7, because 7 isn't available, right? Or 1, 8, 8 isn't available, okay? So as a set, 3, 6, 4, 5, 5, 4, 6, 3. And by the way, an event, as said in the definition, is any subset of the sample space. What's a subset? That's a portion of the sample space. Okay, so every element here that I've got listed in event A can be seen in the bigger set, okay, set S. Be sure that that always happens. Okay, you're not going to have events that are not part of the sample space. Let event B be the event that you roll an 8, right? B is a set. Okay, so what are all the ways that you can roll an 8? Well, you can roll a 2 and then a 6, 3 on the red die and then a 5 on the green die, a pair of 4s, okay, 5 and a 3. Now I actually I've rolled a 4 on the red die and a 4 on the green die. Do I need to switch those? No. Well, I can. See, there's no harm when listing 4, 4 23 times if I wanted to. I would still only count that as one that is different from the others. Okay, so there's no reason to list 4, 4 again. You've already got 4, 4 listed. Okay. Now, flipping these other ones is going to matter. So you can have 5 and then a 3 and then a 6 and then a 2. Okay, so in other words, if a person were to roll a pair of dice, it's more likely they would roll an 8 versus a 9 because there's more ways to obtain an 8. Okay. Part D, let event C be the set listed there. Describe C in your own words. Okay. So I've got a pair of dice, and let's see. I don't see 1, 1 listed, although every other element has 1 as one of the ordered pairs, so exactly one of the dice is going to show 1. Okay, and I think if we word it like that, we've left out the ordered pair 1, 1, which we don't see. Okay, so exactly one of the dice is going to come up with a 1. Definition, an experiment has equally likely outcomes when each outcome has the same chance of occurring. Okay. So in other words, you're not being biased towards any selection. Okay, nothing's being done or known ahead of time. Okay, and any element has an equal shot at being identified there. Another definition: if A is an event, then the probability that A occurs is denoted by the probability of A. Is how we'd read that. If all outcomes in the sample space are equally likely, then the probability of A is defined by the probability of A equals the number of outcomes in A divided by the number of outcomes in the sample space. Okay. A couple of things. By the way, make sure that you're using correct notation. Okay. Be sure that you read on MyMathLab whether the answer should be written in fractional form or in decimal form. Okay, in fractional form, of course, they'll want that in reduced form. In decimal form, if it's a repeated digit, they're going to have to tell you where to round. Okay, so be sure that you've rounded correctly. One of the things that I'm kind of picky about is the probability notation. You always include the event next to the probability sign. Okay, whatever that event is. Like sometimes you got to write out in words what that event is. And sometimes you just use a letter, okay, like event A, okay. Either way, be sure that the event is always next to the probability sign, okay. Now, there's 2 things that always need to happen whenever we work with probability, okay. Number 1, it says if A is an event, then 0 less than or equal to the probability of A less than or equal to 1. In other words, when you compute a probability, you're never going to have something over a 100% chance of occurring. Okay, that's impossible. Okay, also you'll never have a negative percent chance of something occurring. That is impossible. Okay, so if you were to convert these numbers into percentages, you'll always have something that is between 0% and 100%. Okay, so keep in mind, I see numbers that are bigger than 1 more than I should. Okay, the sum of the probabilities of all the outcomes must equal 1. That is, if the sample space consists of the outcomes E1, E2, E3, all up to E sub n, okay, like where was it at? Like this sample space here had 4 outcomes. Okay, so I call it E1, E2, E3, E4. Okay. Then the probability of E1 plus the probability of E2 plus the probability of E3 plus etc. all up to probability of E sub n. So if you were to calculate the probability of every single outcome in the sample space, then you're computing the probability of the sample space, which is always equal to 1. Okay, we'll look at that. These 2 rules, in fact. Problem 9 says that a local golf store sells a bag that contains 80 golf balls in it. Suppose that the bag contains 35 Titleists, 25 max flies, and 20 top flights. Okay, part A, what is the probability that a randomly selected golf ball is a Titleist? Okay, so the first thing, always include the event next to the probability sign. Don't just write P equals. Okay, if you write P equals, my math lab is not going to like that, and it'll probably give you a wrong answer. Okay, so always include the event next to the probability sign. Okay, so we want to find the probability of selecting a Titleist. Well, according to the rule here, I need to take the number of outcomes in the event divided by the number of outcomes in the sample space. Okay, so there's 35 golf balls in the bag that are Titleist brand golf balls, and there are 80 total. So 35 divided by 80 is going to reduce to be, let's see here, 0.35 divided by 0.8. So I'm getting 7/16 there. Okay. Or what would be 0.4375. And I've got a note here. Give your answers using fractions or decimals. Okay, and it's important to read which form that the problem is going to want. Okay. Part B. What is the probability that a randomly selected golf ball is a max fly? Okay, well there's 25 max flies in the bag, 80 golf balls total in the bag, so 25 divided by 80 is going to be 5/16, or that would be equal to 0.3125. Okay, here I've got the fractional form circled. Part C, what's the probability that a randomly selected golf ball is a top flight? Okay, well there's 20 top flights in the bag, 80 total in the bag, so 20 divided by 80 is equal to 1/4. Okay, notice that the 2 probability rules are satisfied. Okay, in problem 9, in general, these rules must be satisfied. Okay, so that's these 2 rules right here. So rule 1 says that every single calculation is going to be a number in between 0 and 1. That's what we've got. Okay, so rule 1 looks good. Now rule 2 says that the sum of the probabilities of all the outcomes must equal 1. Okay, so I've looked at all 80 golf balls in the bag, okay, with these three calculations, since these are the only 3 brands in the bag. Okay, and if I were to add 30/80, or 35/80, plus 25/80, plus 20/80, I would have 80/80, which should be 1. Okay, so the probability of the sample space, that always needs to be 1. Okay, always. Let's maybe do problem 10 and 11. A person can have one of 4 blood types, which are A, B, or O. If a person is randomly selected, is the probability that they have blood type A equal to 1/4? Why or why not? No, because so there's 4 blood types, but the exact number of people that have blood type A is not the same as the number of people that have blood type B or blood type A, B, or blood type O, right? So, in fact, blood type O is sometimes called the universal blood type because almost half the people in the whole world have blood type O. Okay, I think it's like 45% or something like that have blood type O. Blood type AB is the rarest blood type. Okay, I think only 4% of the people in the world have blood type AB. So the fact is that they're not equal in size. Okay, if they were exactly the same size, then yes, it would be 1/4. Okay, but I have said there that no, blood types are not equally likely. Okay. Problem 11. Let the sample space for an experiment be the set of counting numbers 1 through 10, and event F be the event that we have a 3, 5, a 9, or a 10. What is the probability of F? Okay, so event F is a subset of the sample space. That always needs to happen. Okay, and how I define probability is I need the number of outcomes in the event divided by the number of outcomes in the sample space. Okay, so I've got 4 things in F divided by 10 things in S. 4 over 10, reduce that. So 2/5 would be the answer for the probability of F. Okay, and we'll go ahead and stop right there in the notes.